Assalamu alaikum. So we'll continue with the state analysis of synchronous machine. So last time we found the pair phase equivalence circuit for the synchronous machine, and it was very simple. The voltage equation in the steady state condition, VES equal RS IS plus XS IS plus EE, where XS is the synchronous reactance and RS is the stator resistance. So we need a method in order to determine the synchronous reactance and the stator resistance. So let's replot the pair phase equivalence circuit. So this will be the VA plus minus, this will be the RS, this will be the XSJ, and this will be the EA. Now this is the synchronous reactance and this is the stator resistance, and I'm assuming a motor action. Let's say this is IAS. So how to find the synchronous reactance? Simply we need to do two tests. One is the open circuit test and the second one is the short circuit test. So in order to determine the synchronous reactance, the first test that we'll use is the open circuit test. So now the machine, the terminal of the machine, the terminals of the machine are left open, and the shaft of the machine is connected to a prime mover such that the shaft speed is rotating by constant speed, omega equal to omega E, and this one is constant. So now the prime mover is actually the motor, and the synchronous machine is the generator in this case. And simply here we will measure the VA. We will measure VA. So at open circuit test, IA or IS is equal to 0, and VA is equal to EA. Of course, we need to excite the synchronous generator. So this is the field. And this will be the IF. So simply here we can plot the relation between IF and V open circuit. So this will equal V open circuit at constant speed. So at constant speed. Now increasing the IF will increase the terminal voltage until it's saturated. So simply this line here represents the air gap line, and at certain IF, let's assume here, when IF at point A, we're having VA rated, and this point, let's call it C. So the line passing through this point is called the modified air gap line. So this is called the modified air gap line. So this characteristic is called the open circuit characteristic. Now this is the first test. So the second test we need to do is the short circuit. Now in the short circuit test, we have the same configuration. We have the prime mover connected to the shaft of the synchronous machine, and this one is rotating by omega equal to omega s, which is constant. And we are shorting the terminals. So here we can measure the current. So VA will equal to 0 and IA will equal to I short circuit. So from the voltage equation, 0 will equal Z IA plus EA. So IA can be measured and EA can be found from the open circuit test. So we can find the Z. So we can find the Z. So simply here can be measured, and EA we can get it from the open circuit test or from the graph of the open circuit characteristic. So Z as a magnitude will equal EA over IA, and this will equal the square root of RS square plus XS square. So we need to find RS in order to find XS. So XS will equal to the square root of Z square minus RA or RS, let's say I'm using RS square. So how to find the stator resistance? This is very simple. We will go to the machine and connect a DC source to two terminals, and we'll measure the current and the voltage. So we know that R total here will equal to V over I, and R total will equal to RS, because simply we have two coils in series in this case. If we plot it here, so simply here this will be RS, this will be RS. So now RS will equal 1 over 2 VDC over I DC. If we substitute here, we can find XS. So the short circuit characteristic, we can plot it here. Let's assume this is the axis representing IS. So this will be the short circuit characteristic. Now at certain point, let's assume at point E, we are getting here IA rated. Now we need to have this value, the current IA at this value, IA at B, let's say. So we can calculate the impedance Z, this Z. So Z will equal ECA over IBA at omega equal to omega S. So ECA is this one, VA rated, and IBA is this current. So we need to register this current, and we need to register this voltage in order to calculate the impedance. And for the resistance, it's simply from the well-known DC voltage test, in which we are supplying a small voltage such that the current in the coil is equal to the rate. Then simply the RS will equal 1 over 2 VDC over IDC. So let's discuss the following example. Uh, 200 kilovolt ampere, 480 volt, 50 hertz, Y connected, synchronous generator, with a rated field current of 5 ampere was tested, and the following data was taken. The first one, V line to line open circuit at the rated field current was equal to 540 volt, and the second test, the I short circuit at IF rated was equal 300 ampere. The third test, when a DC voltage of 10 volt was applied to two terminals of the machine, a current of 25 ampere was measured using ampere meter. Now we need to find RS and XS. Now simply we have all the information. The first test here is the open circuit test. The second test here is the short circuit test, and the last test here is the DC test. So the first thing here we can calculate is the resistance of the stator. So we have the following relation: 2 RS is equal BDC over IDC. So this will equal 10 over 2 multiplied by 2.5, and this will equal 0.2 ohm. Now EA will equal V phase open circuit, so this will equal 540 over square root of 3, and this will equal 311.8 volt. Now given I short circuit equal 300 ampere, so simply from here we can calculate the amplitude of the Z, which will equal the square root of RS square plus XS square, and this was equal to 311.8 over 300. This equal to EA over I short circuit, and if we do the math, this will equal 1.039 ohm. So we have RS, so we can calculate XS, which will equal the square root of 1.039 square minus 0.2 square, and this will equal 1.02 ohm. Note that if RS is negligible, actually it's very small, then XS will equal to the Z, which equal 1.039. So let's assume that for simplicity that RS go to 0. So if RS go to 0, then the voltage equation now will read as VAS equal to EA as a phasor plus JXS IAS as a phasor. So This will be a very simple circuit. VA JXS EA, and this is the convention of the motor action, so this will be the IS or the IA. Because here I'm using A, let's say IA. So let's assume that I will plot the Phasor diagram for this simple circuit, assuming constant power. So let's assume constant power. So for constant power. Now let's assume this is my reference, which is the V terminal, VA. And let's discuss the following scenarios. The first one is the lagging power factor. So the first one here I will discuss is the one which is the lagging power factor, which means that the synchronous machine is consume reactive power from the grid. So simply this will be the IAS, and this is theta, it's lagging, and IA cosine theta will be constant, because we are assuming a constant power. So if we need to calculate the EA, we need to solve this equation. So EA will equal to VA minus J XS IAS. So this will be the minus AS. So this will be the minus XS IAS, and J will rotate this vector 90 degree pi over 2. So simply we will have this one, which is the minus J XS IAS, and now this will be EA. So this will be EA. This is for lagging power factor. Now for unity power factor, here for unity power factor. Now for unity power factor, the IA and VA are in phase. So simply this will be the direction of the minus A XS, and this will be the direction of the minus IA XS, and the J will do the 90 degree. So simply we'll have it here. So this one for a unity power factor. Now for the leading power factor, so here for leading power factor, so this is the current here for leading power factor. and the vector in the negative will be somewhere here, and 90 degree will be in this direction, and this will be the EA. So this is the phasor representation for the synchronous motor under different power factor. Notice here, due to the assumption that the power is constant, this one will be constant, and also this one is constant. So I think we should replot it here, and let's start with this is the IF, and this is the IA, and also here I can plot the power factor. Those are normalized. So simply for different IF we can achieve leading power factor, unity power factor, or lagging power factor. So let's assume here for IF1 and IF2 and here IF3. So this will be the lag power factor, this will be the lead power factor, and this is the unity power factor. Now IA, this will be the IA. So this is a plot, of course, at constant speed, at synchronous speed. So the field current can be adjusted such that IA lead VA. So in this case, the machine appear as a capacitor, supplying reactive power to the system. So simply, if IF is adjusted such that IAS lead VAS, then the machine appears as a capacitor, supplying reactive power to the system. Now, this in the case if IF is adjusted such that IAS leads BS. Now, we can also adjust IF such that IAS lags VAS. In this case, the machine will absorb reactive power from the system. From the system. So simply this means that the machine, the synchronous machine, can be operated in unity power factor, in leading power factor, or in lagging power factor by adjusting the excitation or the field current, by adjusting the excitation or the field current. So let's replot the phasor representation. The first one here, I will do it in detail. This is the V terminal or VA. And let's assume that I'm discussing a lagging power factor. So here I'm discussing the lagging power factor, and I'm assuming a constant power. So I'm assuming here constant power. So for lagging power factor, this means that the current will lags the voltage. So let's assume this is IAS and this is the theta. So here theta is negative, lagging power factor. And now we need to calculate the internal voltage or the induced voltage or the back EMF voltage, which is EA. So we need to evaluate the voltage equation. So VA equal to JXS IA plus EA. So EA will equal to VA minus JXS IA. So the first thing here, I will evaluate this one. So XS IA in negative. So this actually is in the opposite direction of IAS, scaled by XS, and let's assume it's here. So this is also theta. So this one actually is minus XSIA. Now the J operator here will rotate the vector counterclockwise 90 degree. So this one will rotate the vector 90 degree or pi over 2 counterclockwise, in counterclockwise direction. So counterclockwise direction, it will be somewhere here. So this actually is minus JXSIA. So if I'm closing the triangle here, I'm getting this is the EA and this is delta. So this is how we are plotting the phasor representation. So now I will do it here for all the cases, for the lagging power factor, for the unity power factor, and for the leading power factor. And for that, I will use red for the lagging power factor, and I will use black for the unity power factor, and I will use blue for the leading power factor. So let's start here. So the terminal voltage here is V terminal, this constant, and let's start with the lagging power factor. So let's assume this is IA. So this will be minus j I a xs. Let's assume this is 1, so this will be the 1, and this will be the EA1, and this will be the delta 1. And remember that the red for the line for the lagging power factor. Now, for unity power factor, we use the black for that. So unity power factor here. We are assuming that the power is constant, so this means that IA cosine theta must be constant. So the power is constant. Then IA cosine theta must be constant. Why? Because V terminal is constant, and we know that the power in three-phase system, the power N is equal 3 VA IA cosine theta. So simply this one from here to here must be constant. So because we are assuming constant power, then this will be the IA in the case of the unity power factor, and this will be the minus j IA2 xs, and this will be EA2. Now for the leading power factor, and we use, I think, the blue for that, for blue line for the leading power factor, and IA cosine theta must be constant, so it must be somewhere here. So this will be the IA3. Now the projection will be here. This will be the minus. This will be the minus j IAS3 xs, and this will be EA3 in the case of the leading power factor. Now here the same observation. This one actually is EA sine delta. EA sine delta. This projection here is actually EA sine delta, which also will equal to IAX cosine theta. So because this is also projection, now let's make it more clear. This one from here to here is EA sine delta, and this also, because this angle is theta, this also equal to IAX cosine theta. So this also equal to IAX as cosine theta. Now this is the line here, so this will be theta. So from the Phasor representation, we stated that EA sine delta will equal to the IA XS cosine theta. Let's recall that this angle is equal to this angle. Let's use the same color. This angle here is equal to the same angle. So simply this vector is IAXS. So the projection will be equal to the cosine. And the same thing, this angle here is delta 3. So this will equal EA3 sine delta 3. So simply we have the following relation, which is that for constant power, EA sine delta is equal IAX cosine theta. So if we multiply the both sides by VA, the terminal voltage, we are getting VA EA sine delta is equal VA IA XS cosine theta. If we divide by the synchronous reactance, so this will be VA EA over XS sine delta is equal VA IA cosine theta. If we here multiply by 3, here we should multiply by 3. So simply this is actually the power. So the power will equal to 3 VA EA over XS sine delta. Now the torque will equal the power over omega m. So this will equal 3 over omega m VA EA over XS sine delta, and those all in magnitude. So this is magnitude, magnitude, and magnitude. And this is the torque actually for synchronous machine. And to be specific, this is for cylindrical machine where there's no double frequency of the rotor angle. So if we need to plot the power and the torque with respect to the rotor angle delta, so this will be the sign for the power, and for the torque it will be scaled by XS. Let's assume XS is greater than 1, and this will be the torque. So from here to here, this will be the generator action, in which delta is positive, and from here to here, this will be the motor action, in which delta is negative. Now the maximum power or the maximum torque will appear at pi over 2 minus pi over 2. Now we can use the synchronous motor actually in a factory in order to support or correct the power factor. And for that, let's assume we have the following example. I will solve 2 parts and I will let the remaining parts for you as exercise. Let's assume we have a small industry facility. So here a small industrial facility consists of grid system here. We have infinite bus, let's say. Connected to 3 loads. The first load consume 100 kilowatt at 0.9 power factor lagging. So can represent induction machines, let's say. The second load this load number 2 consume 80 kilovolt ampere at 0.8 power factor, also lagging. And finally here we have synchronous motor. And here we have switch in which at any time we can connect the synchronous motor to the facility, and this will be the I3, and the rating for the synchronous machine has rating 100 horsepower, 460 volt, 0.8 power factor leading, and we have XS equal to 1.1 per unit, and the RA or RS equal to 0.01 per unit. Those reactance and resistance are calculated at the rated value of the machine, of the synchronous machine. And now we need to solve the following cases. Case number 1. The switch is open. We need to calculate how much real power, reactive power, and apparent power is being supplied to the plant. So, how much real power, reactive power, and apparent power are supplied to the plant, and we need to calculate the total current IL. So this will be the IL. Now, how to solve it? Simply here we have 2 loads because the third load is switched off. So for load number 1, we have P1 equal to 100 kilowatt. This is given. So from here we can calculate Q1, which equal P1 tan inverse of tan of cosine the inverse of the power factor. Now, if you remember the power triangle, this is the P, this is the Q, and this is the S, and this is the power factor, theta. And we know that the power factor is equal cosine theta. So if we need to find theta, this will be cosine inverse of the power factor, and Q will equal P1 tan theta, because tan theta is Q over P. So from here we can calculate Q1, which will equal 48.4 kilowatt. Now for the second load, P2, second load, what's given? The second load, it's given the apparent power. So this is the S, and this is the P here. Huh? So this is the S. So simply from here, we know that P is equal S cosine theta, and Q is equal S sine theta. So B2 is equal to S2 cosine theta, and if we do the math, this will be 80 multiplied by 0.8, so this will equal 64 kilowatt, and Q2 will equal to S2 sine theta, and theta here is cosine inverse of the power factor, so this will equal 80 multiplied by sine of cosine of the inverse of 0.8, and this will equal 48 kilowatt. So now the power total consumed by the facility is equal P1 plus P2, which will equal 164 kilowatt, and Q total equal to Q1 plus Q2, which equal to 48.4 plus 48, and this will equal to 96.4 kilowatt. So S total is equal to square root of P total square plus Q total square, and this will equal 190.2 kilowatt. Now the line current, IL is equal to S total over square root of 3 VL, and this will equal 190.2 over square root of 3 multiplied by 460, and simply you can do the math here. So if we calculate this one here, if we do the math, this will equal 238.7 ampere.